Hey folks, today we're going to talk about work and energy, and hopefully you have the energy to follow along with me. Uh, this is a topic that you all would have covered last year, uh, and it's not easy. Conceptually, it's a little trickier than talking about motion or distance or forces even. You know, force is simply a push or pull. You can kind of picture that. Work and energy, not so much. Okay, it's a little trickier conceptually. So today's discussion is going to be a lot of conceptual stuff. There will be some math here, but I'm going to focus on and emphasize the conceptual part of it. All right. Now, normally I don't do this, but for now, I'm going to actually start with an equation, and that's called the work energy principle. Okay. And let's start with work. Okay. Work, the symbol for work is a capital W, and it's measured in joules, or a capital J. Okay. Now, if you were to look in a textbook, let's say, or online or something like that, and you were to look up definition of work, and we're talking mechanical work here or physical work, your textbook would probably say something like this: work is a change in energy. Okay. So then hopefully you would naturally look up, well, what's energy? Okay. So then you would go look that up. What's mechanical energy? And if you look that up, it would say something like the ability to do work. Wow, that's helpful, right? Okay. And again, partly because work and energy is kind of a complicated topic, okay? So we're going to focus right now on something called kinetic energy, which you would have talked about last year. And it's the energy of motion. If something is moving, it's got energy. The more massive it is and the faster it's moving, the more kinetic energy it's got, okay? Well, it turns out that if you add up all the work you do on an object, okay, the net work now, so we know sigma means net sum of all the work done, that's going to equal a change in kinetic energy. Now, I'm only using a K here. Last year, you probably would have used KE. When you go into advanced science, you don't put KE anymore. You just put K. So this is kinetic energy. Okay. Now, the two other symbols that are absolutely important here is a delta means change, right? So if you wrote work equals kinetic energy, that's totally wrong. No, the net work equals a change in kinetic energy. And I'll even put that's the sum of, right, or net for the sigma, okay? Now, because there's an equal sign here, both work and energy are both measured in joules. They have to be measured in the same units, okay? Now, I'm going to come back and talk about this equation in a little bit here. We're going to do an example with it. But in order to figure out work, okay, the next thing I need to talk with you about is a mathematical concept called dot product. So I'm going to do that over here, okay, dot product. Okay, now, for now, I'm going to give you some basic stuff about dot product. In a subsequent video, I'll talk a lot more in depth about it. But a dot product involves vectors, okay? And it's what you look at how two vectors' directions compare to each other. And when I first learned dot product, I learned the equation for it first, and I wish I hadn't. I wish somebody would have told me the conceptual part first, so the equation would have made a lot more sense to me. So here's dot product, okay? Let's say you got a vector A and you got a vector B. Okay, there they are. The dot product is simply the measure of how parallel those two vectors are to each other, okay? Now, a dot product can be a plus, a minus, or a zero, okay? Now, if you look at A and B, they're not parallel, but like a component of B is parallel to A, right? So you would have, in this case, a positive dot product, okay? So the vector dot product is a measure of how parallel the vectors are. Now, I'm going to give you three quick examples and ask you just to think about would they be a max positive, a max negative, or a zero. So let's say we had A and B, and they were oriented that way. Would you expect a max positive, a max negative, or a zero answer for dot product? Well, they're parallel to each other, so hopefully you're saying max positive, okay? Now, what if I did this? What if I had A going that way and B going that way? So now they're perpendicular to each other. Well, no part of B is parallel to A at all. So if I asked you what's A dot B, hopefully you would say zero, okay? And finally, what if I had A going this way and B going that way? Okay, what would you say then? What's A dot B, max positive, max negative, or zero? Well, they're opposite each other. So hopefully you'd say negative, Okay. Now, if you understand that, the rest of this discussion is going to be pretty easy for you. Okay. So dot product is pretty simple. Now, if you ask yourself, hey, what trig function is a max positive at 0 degrees, because those are at 0, 0 at 90 degrees, and a max negative at 180, hopefully you're saying to yourself, hey, that's cosine, right? Cosine of 0 is 1, cosine of 90 is 0, and cosine of 180 is negative 1. Okay. So it turns out dot product involves cosine. Okay. And specifically, the equation, and I'll write this down now, you would kind of write it like this. A dot B is equal to how big A is, magnitude of A, times the magnitude of B, times cosine of the angle between them. Okay. Now, for us, for now, we're just going to use kind of the right-hand side of this. So if I told you that A was 5 units long and B was 4 units long and this angle were 30 degrees, you would take 4 times 5 times 20, cosine of 20, and that would be your dot product. Okay. Now, why do I bring that up? Okay. Well, to calculate work is done by forces. Okay. Pushes and pulls provide work. Okay. And the equation for that work, and you would have done something like this last year too, the work done by any individual force is force dot, now notice it's not just times, it's dot, I'll make a note of that, is dot, delta R. Okay, now I use R here. It could be a delta X, could be a delta Y, but I'll use delta R because this could be a two-dimensional problem, okay, which we will do. Okay, so another way to write that would be the magnitude of the force times the magnitude of delta R, okay, times cosine of the angle between them, okay. Now, I don't want you to harp on the cosine. What I really want you to focus more on is the conceptual part, okay. Is my answer positive, negative, or 0? And you don't need a math function to tell you that. You can just look at the two vectors and figure out if it's a max positive or if it's a positive, negative, or 0. Okay, I want you to focus more on that than always plugging in cosine. Okay, all right. Now, the units for work, as I mentioned before, are measured in joules. Okay, just like kinetic energy is. And the key here is, let's say multiple forces are acting on an object. Well, then you're going to have multiple work terms, and if you add up all those work terms, that becomes your net work in the work energy principle. Okay. Each force could provide positive work, negative work, or 0 work. And one way to think of that is the force trying to speed the object up, is it trying to slow the object down, or is it trying to just hold the object in place or keep it from moving faster or slower? Okay. And as far as energy goes, here's how I kind of think of it. I think of energy as like a fluid. And you're either adding it to the object or you're taking it away from the object. And that fluid is what makes the object move. Okay, that's your kinetic energy. So you can have forces adding fluid to the object, making it speed up, or you can have forces taking fluid out of the object and slowing it down. So that's one way to look at it. Okay. All right, now the next couple examples are totally conceptual. You feel free to write this stuff down if you want. I'm going to kind of talk through it. So I've got a picture of a desk here and a picture of a book. Okay, here's a desk, here's a book. Now, I'm going to ask you questions about positive, negative, and 0 work. Okay, that's all I'm going to focus on right now. All right, so let's say I had the book, and let's say it starts from rest, and I lift it up and put it on the table. Okay, and it's now at rest again. Okay. Was there any work? Was the work done positive, negative, or 0? Okay. Now, if we were in class right now, I'd have people raising their hands, and they'd be asking what they thought, and there'd be people that would probably be saying positive work, and that's sort of right. But eventually, one of you would probably come to the conclusion like, "Hey, Mashar, you're not giving me enough info." All right. How many forces are acting on the book when it moves from the floor to the tabletop? Okay. Well, as the book moves from the floor to the tabletop, here's your hand. That's the normal force, we'll call that. And there's a force of gravity. Okay. All right. So while the book was moving up, that's your displacement, that's your delta R. Okay. The normal force was up. So the normal force did positive work. On the other hand, the force of gravity was down. So how does the force of gravity's direction compare to delta R? Well, they're opposite. So the work done by the force of gravity would be negative. All right. And then what if I asked you for the net work? Okay, well, check this out. Kinetic energy is the energy of motion. Before we started moving the book was not moving. It had no energy of motion. And when we're all done, the book is not moving anymore, so the book has no energy of motion. So its kinetic energy before and after the motion is zero. Therefore, the change in kinetic energy, got to be zero, right? 0 minus 0. So what's our net work? Well, the net work is zero, okay? So you had work done by the normal force, which is positive, work done by gravity, which is negative. Because of how we move the book, the sum of those is zero. In other words, if you're lifting the book at a constant velocity, the normal force and gravity are going to equal each other anyway, and so they kind of like their works kind of cancel out. So if I ask you what's the work done, you got to be specific. Is the work done by which force is the work done by, or is he asking me for net force? Okay. Now I got another one. All right. Let's say I take the book, okay, and I slide it across the table. So it starts from rest. I push it with my hand. And then I let it stop here. Okay. All right. Is work done positive, negative, or zero? All right. Well, hopefully you're asking yourself, hey, which force is Mashar talking about? Okay. So in this case, now it's a little more complicated. I got 4 forces acting on this book. I got your hand, which I'll call I'll call that an applied force just for fun. Now the book stops because there's friction, right? Okay, so we got that. We have our normal force and we have gravity. Okay, well, let's start with the normal force. Does it do any work? Well, the answer is no, because delta R was this way, right? So the normal force is perpendicular to delta R, so the normal force doesn't do any work. All the normal force does is hold the book in place. Same goes for gravity. It does zero work. Okay, so those are gone. How about the work done by the applied force? Well, that's in the same direction as delta R, so that's positive. How about the work done by friction? Well, that's the opposite direction of delta R, so that's negative work, okay? And what's our net work? Well, the book started from rest and it ended at rest, so the starting kinetic energy is 0, the final is 0, so the change is 0, so your net work is 0. Now, the net work's not always 0, don't get me wrong here. So for instance, if I push the book really hard, it's going to accelerate, and there the net work would not be 0. We're going to have problems like that too. But for this example, because I let the book start and stop, the net work is indeed 0. Okay. Now, what if you're just holding the book? So let's say you're standing here, right, and your arms are out, and you are just holding the book. Okay, so you're just holding it in place here. Okay. Is there any work done? By the way, that's a pretty big textbook, right? All right, is there any work done if you're just holding it there? Well, it might feel like it to us, right? But it turns out the answer is no. You are applying a force, but you are not doing any work at all, okay? You have to have a displacement in order for work to get done, okay? You have to move it somewhere to do work, okay? Now, I am going to do one math example here. So let's say I take the book. Here it is. And let's say that it's 2 kilograms and it's on the floor or the desktop, whatever, either one, okay? And let's say I pull it with a force applied of 20 newtons, okay? Let's say the coefficient of kinetic friction between the book and the tabletop is 0.4, okay? Let's say the mass of the book is 2 kilograms. That'd be probably a fairly average size textbook. And let's say you do this over the course of 5 meters. Okay, it's about 16 feet, so like across the room, let's say. All right, here are some things we're going to calculate briefly. This will be very fast. We're going to find the work done by the force applied. We're going to find the work done by the force of friction. We're going to find the work done by the normal force. We're going to find the work done by the force of gravity, and then we're going to find the net work. Okay. Oh, and then finally, we're going to find the change in kinetic energy. Okay. All right. Well, it would probably help to draw an FBD. So here's our book. You got an applied force, which is 20. You got force of gravity. you got force normal, and you're going to have the force of friction. And I'll go ahead and calculate that really quick. The force of friction is going to be mu Fn. Hopefully you'll notice in this problem that Fn and Fg are going to be equal because the book's not accelerating up or down at all, and there's no other vertical forces. So you got mu mg. And if you plug in 0.4 times 2 times 9.8, you should get, I get 7.84 newtons, okay? All right, we don't need to calculate the normal force and gravity, or if we do, we'll do that in a minute. That should be 2 times 9.8, which would be 19.6 newtons. I don't think we're going to need that, though. All right, work done by the applied force. That's this guy here. Well, remember, delta R is to the right. Okay, that's which way the book moved. So is that going to be positive, negative, or zero? Well, it's positive. And then we're going to take force times delta R, okay, which is 20 times 5, and it's positive 100 joules. Work done by friction, positive or negative? Well, that's acting in the opposite direction of the motion, so that's going to be negative. Force of friction delta R, which is negative 7.84 times 5, which is negative 39.2, I think my calculator says. You might want to check me there, but I believe that's correct. How about the work done by the normal force? Well, that's perpendicular to the motion, so there's no work done, so you just put a 0 there. How about the work done by gravity? Well, that's also perpendicular, so that's a 0 there. What's your net work? Well, net just means add them up. So what's 100 plus negative 39.2? You should get 60.8 joules. And what's your change in kinetic energy? Well, net work is a change in kinetic energy, so hello, it's also 60.8 joules. Okay. Now, that was a really simple problem. Don't worry, they'll get tougher. The next example is a video example where I got the book on an incline and I'm pushing on it, so it gets a little trickier. But the keys on this, is the work positive, negative, or 0? And you don't need a calculator to tell you that. Just look at it, and it's going to make a lot of sense to you. I really actually suggest you put the calculator down for a moment and think about what's happening before you pick it up and do your calculations. All right, I hope that was helpful, and I'll see you again next time.